In this video, we'll look at some new developments in choosing camera locations for a single survey. In particular, we'll look at two papers that try and optimize the placement of cameras for SCR surveys. In the last few videos, we looked at some guidance that's very well established and has been used in dozens of SCR surveys. In contrast, the two papers that we'll look at have come up in the last few months. That means that although they have the potential to deliver statistically better designs, you want to use some caution when using these new methods. So just to recap where we are, the goal of micro-level design is to choose camera placements for a single survey. We're not going to tell you exactly where to place the cameras, so next to which scratching post or next to which path. Rather, what we're going to do is to take the survey area and divide it up into grid cells. Here, something like 1.5 by 1.5 kilometers. And the goal of micro-level design is to choose the grid cells that we're going to visit. After that, it's up to the individual researcher to choose the best camera placement in the selected grid cells. The purpose of the design is to come up with a selection of grid cells that allows us to estimate abundance or density precisely and without bias. So there's a very clear statistical objective to our design. To avoid bias, we know that we need to avoid preferentially sampling good or bad habitats, and to try and get precise estimates, we're trying to boost the sample size that we gain from our survey. And that means balancing the number of unique animals that we see and the number of recaptures that we get. We also looked at a couple of designs. So here, the cameras are placed way too far apart. That means that although we'll get many unique animals, we're going to get hardly any recaptures, and so this is bad for estimating sigma and therefore for estimating density. In contrast, here the cameras are placed way too close together, and this means that although we'll get plenty of recaptures, we'll probably only capture one or two animals, and this is way too few for an SCR model. So the fact that we've got some designs that are way too far apart and some designs where the cameras are way too close together suggests that there's some kind of an optimal balance between them. In both of these designs that I've shown, the cameras are in regular grids, but that doesn't have to be the case. Cameras could be placed anywhere. So this raises the question, can we choose camera placements that are optimal in some way? This is the question that these two papers try and answer. They set out to develop methods for optimal placement of camera traps for SCR surveys. Both of the papers use snow leopards as a case study, and if you look through the list of authors, you'll see some people that work for snow leopard organizations or consulting statisticians for those organizations. The two papers are very similar and complement one another. Before I talk about the differences, I'm just going to talk about their similarities. To start with, we need to define a set of possible camera locations. So, for example, we might specify the midpoint of each of these 1.5 by 1.5 kilometer cells. This is a bit of a more advanced point, but we need to be a little bit careful here. We don't want cameras to be placed very close together. And the reason for this is basically that recaptures at very small distances are not that informative. So we need to make sure that the gap between our possible camera locations is not that small. So for example, here, even if we're going to use a mesh with grid cell size 1.5 by 1.5 kilometers, we might place 3 kilometers between our possible camera locations, just to make sure that cameras are not placed too close together. In this case, I'm using an example of 4.5 kilometers for sigma, and so 3 kilometers works out to roughly 2/3 of sigma. We'll land up with a set of hundreds or thousands of possible camera locations, whereas we'll only have 40 or 60 cameras, say, to go around. So what we'll now like to do is to pass these possible camera locations to an optimization algorithm and let it decide out of the thousands of possible camera locations which are the 40 or 60 or 80 sites that we should put our cameras at. In order to do this, we're going to use an optimization algorithm. And so I'll quickly walk you through the basics of an optimization algorithm. Say we've got a complicated function that we want to find the minimum of, but only using stupid computational operations, nothing fancy like derivatives or anything like that. One thing we could do is to start with an initial random solution, and then we could perturb this initial solution by a little bit. Here, that's an improving move because it's downhill. And we could carry on perturbing the solution by a little bit, evaluating whether it's good or bad each time by plugging it into the objective function. eventually we'll move along the solution space and land up in what we hope is a global minimum. We'll never know if it's an actual minimum, an actual global minimum for sure, but we can explore the solution space in this way. This is one kind of optimization procedure. A different kind, and this is actually the kind that gets used in these two papers, is to use a population of initial solutions. So we can start by generating a whole bunch of initial solutions and evaluating how good or bad they are by plugging them, each of them, into the objective function. We can then identify the good initial solutions, and we can combine these solutions in some way to create a second group of solutions. And these will have properties that are more similar to the good solutions in the previous round than to the bad solutions. And if we carry on this procedure, so identifying out of this second round the good solutions and allowing them to pass on their characteristics to the next round, we'll eventually land up in what we hope is a good part of the solution space. This is the basic idea behind a genetic algorithm, which is the optimization approach used in both of the methods that I'm explaining. This particular example has got nothing to do with camera traps or SCR, but it hopefully explains the way that genetic algorithms work. Now, when we're talking about camera trap designs, each of these possible solutions is going to be a potential design, and the question that we need to ask ourselves now is how are we going to evaluate the quality of a design? So what are we going to use as an objective function? This is the main difference between the two papers. The paper on the left tries to maximize the probability of seeing an animal exactly twice. The rationale behind this criterion is that seeing an animal once gives you a unique capture, whereas seeing an animal twice or more gives you recaptures. And so this tries in a heuristic way to balance the competing goals of getting unique captures and recaptures. The paper on the right proposes an objective function that tries to maximize whichever is currently smallest, the expected number of animals detected or the expected number of recaptures. And the rationale behind this criterion is that there's a direct link between it and the variance of density estimates given by this approximation. The idea is that by optimizing what's on the right, we also optimize what's on the left, and this is a statistically well-defined objective function. You can develop designs using either criterion using the R package OSCR, and both papers contain code examples for doing this. Let's finish up by looking at an example. This is a design that we looked at in one of the previous videos. We said it was pretty good, and it's definitely much better than the two designs that we started out this video with. It's expected to return 19.2 unique animals and close to 35 recaptures, and that gives an expected CV of density estimates of around 23%. If we use the second objective function, the one that tries to minimize the CV of density estimates, to try and balance the expected number of unique animals and recaptures, we land up with a design that looks like this. That returns 28 unique animals and 28 recaptures in expectation, so it's balanced these two. And that improves the expected CV of density estimates from 23% down to 19%. This design assumes that density is constant throughout the survey region, but the optimization procedure can account for spatially varying density. Say we have elevation information and we expect density to be positively correlated with elevation. Here, high elevation areas are in light blue and low elevation areas are in dark blue. If we feed this covariance information into the optimizer, you'll see that it places most of the traps in high elevation areas, and that's because that's expected to return a greater number of unique animals and recaptures. Here we have to be really careful. This design only tries to optimize sample size, so it tries to find the positions of cameras that give us the most unique animals and recaptures. However, if we're going to model density as a function of covariates, we know from the previous videos that we need to cover a range of covariate values. So we need to have both high elevation and low elevation sites. Here that's not the case because all of the cameras have been placed in high elevation sites. So we'd need to augment this design by placing some of the cameras in low elevation areas. However, it's a useful starting point for those kinds of discussions. So just to summarize what we've done with this video, we know from previous videos that the overall goal in designing SCR surveys is usually to estimate abundance precisely and without bias. These are both statistical criteria that we can formulate mathematically, and so they're ideal criteria for optimization. Some new papers in this area have developed methods for optimizing these objective functions. These new methods that optimize camera placement have the potential to increase sample sizes and so improve the estimates of SCR models. They're all very new though, so it's really important to proceed with caution. Always check all your answers with simulation and consult a statistician if you're in any doubt about the methods.